Cikan is a sport native to the Indigenous tribes of Saskatchewan and was often played by young Indigenous children. In this game, the players start off by swinging a rope with a rawhide pouch and a ball in it in a circular motion and then let it go. The whole purpose of this game is to see who can launch the slingshot the furthest horizontal distance. This game helped the Indigenous kids to practice hunting techniques as the skills developed in the game to Wepi were directly transferable to the skills they would apply while hunting. During this video, we will be dissecting the sport of Tuepi and explaining how it relates to physics. Projectile motion is the main kinematics topic explored in the sport Tuepi. Projectile motion can be described as the motion of an object when launched in the air with only acceleration due to gravity acting upon it. With projectile motion, the vertical and horizontal components of velocity while the object is in flight create what is called the resultant velocity. The vertical component of the object's velocity is constantly changing while the horizontal component remains constant throughout the object's flight. This is because gravity acts in the vertical direction. The projectile motion of the object in Tuepi is not perfectly symmetrical because the ball is launched from a height. This means that the velocity the ball hits the ground with will be of greater magnitude than the velocity it was initially launched with. The projectile motion of the slingshot will differ based on how it is released. Here's the trick I use that helps me win almost every time while playing this game. In order to launch it the furthest horizontal distance and give yourself the best chance at winning, you want to release the slingshot at an angle of 45 degrees above the ground. This will maximize the horizontal distance because the vertical and horizontal components of the object's velocity will be equal. Another thing to consider when playing the sport is how acceleration due to gravity affects the projectile motion of the slingshot. If this sport was played on Mars, which has a much smaller acceleration due to gravity, only about 3.7 meters per second squared, the slingshot would travel a further horizontal distance. This is because if acceleration due to gravity increases, the time of flight decreases, and so does the horizontal distance.
I will now be doing a calculation on the velocity of the ball relative to the ground. I start by listing my variables and positive directions. The equation for the velocity of the ball relative to the ground is the velocity of the ball relative to the wind plus the velocity of the wind to the ground. I can then use this information to create my vector diagram. I split my vectors up into north-south components and east-west components. This is where you use the vector diagram to conceptualize which values will be negative and which will be positive. In this case, for this value I'm calculating right now, it is a negative value. I use these resultant vectors to create a right triangle where the hypotenuse is the velocity of the ball relative to the ground. I use the rearranged equation of the Pythagorean theorem to solve for the magnitude of the velocity. I now only need to calculate the angle by rearranging for theta in terms of tan. I use the east-west component as my opposite value and north-south as my adjacent value, then multiply it by the inverse of tan. I now make my therefore statement and apply significant digits. Therefore, the velocity of the ball relative to the ground is 39 meters per second north, 36 degrees east. I will now be doing a calculation on the 2D acceleration of the ball and change of velocity after it contacts the ground. I begin by listing my variables in positive directions. I have also added a diagram. The change in velocity is equal to the final velocity subtract the initial velocity. I draw another diagram known as a vector diagram to represent the equation where the resultant velocity vector is the change in velocity. I split my vectors up into up-down components and right-left components. Again, I use the vector diagram as a visual to determine which values are positive and which are negative. I then add up my vertical and horizontal components to get the resultant vectors of each. I use these vectors to create a right triangle where the hypotenuse is equal to the change in velocity. I then rearrange the Pythagorean theorem to determine the magnitude of the change in velocity. Finally, my opposite vector divided by my adjacent vector, then multiply it by the tan inverse to solve for theta. I can now use the change in velocity to solve for acceleration. Acceleration is the change in velocity over a unit time. I plug both these variables into the equation and get my final answer for acceleration. The direction for acceleration is the same as the direction for the change in velocity. I now create my therefore statement and apply significant digits. The acceleration of the ball once it contacts the ground is 4.5 times 10 to the 2 meters per second squared up 1 degree to the right.
The slingshot being swung before it is released represents uniform circular motion. This is because the radius of the slingshot and angular velocity remain constant until it is released. The sport to Wepi Cikan relates to all of Newton's laws in some way. Newton's first law is the law of inertia, which states that an object at rest or moving at constant velocity will remain to do so unless struck by an imbalanced force. The ball in the rawhide pouch at the end of the slingshot has inertia. This is because the net force acting on it is zero due to the balance of forces acting on it in all directions. This causes it to move with constant angular velocity. It loses its inertia once the slingshot is released. Newton's second law states that the net force of an object is equal to the product of its mass and acceleration. This creates the relationship that the acceleration of the ball in the rawhide pouch is inversely proportional to its mass and proportional to the net force, or centripetal force. When in circular motion, increasing the net force on the ball will increase centripetal acceleration, and increasing its mass will decrease its centripetal acceleration. Newton's third law states that for every action force, there is an equal and opposite reaction force. This is seen in the sport to Wepi Cikan when the ball is in circular motion. The centrifugal force provides an equal and opposite reaction force to the centripetal force, which is what keeps the ball in circular motion.
The force of static friction is present and keeps the ball stationary in the rawhide pouch when the pouch is not parallel to the ground while in circular motion. When it is parallel to the force of gravity, it applies a force equal in magnitude but opposite in direction to the force of gravity, just as Newton's third law states. In this calculation, we are calculating for the force of static friction when the pouch is in circular motion and parallel to the force of gravity by equating the two forces. I can now write my therefore statement by saying the force of static friction on the ball when parallel to the force of gravity is 5.9 newtons up. To calculate the force of tension in each string when the ball is at the top of circular motion, I start by listing my variables and declaring up as positive. The net force is equal to the centripetal force and also equal to the force of tension subtract the force of gravity. When I rearrange, I get the force of tension equal to the difference between the centripetal force and the force of gravity. I then plug in my variables to solve for the force of tension. I divide this force of tension by 4 because my rawhide pouch was attached to 4 identical pieces of string. I can now write my therefore statement. The force of tension at the top of circular motion in each string is 2.5 times 10 to the 2 newtons.
We will now be talking about energy and momentum and how it relates to the sport Wepi Cikan. The law of conservation of energy can be observed during the sport Wepi Cikan. The law of conservation of energy states that in an isolated system, the net or total energy always remains constant. This is because energy cannot be created or destroyed, but instead is just transferred to alternate forms. It can be observed during the sport Wepi Cikan when the slingshot is being swung in a circular motion. At the top, it has very high potential energy, and at the bottom, that potential energy is lowered. It can also be observed from when the slingshot is released to just before it contacts the ground. Once the ball contacts the ground, the law of conservation of energy can no longer be observed. This is because the system is no longer isolated, and once the ball hits the ground, some energy is lost from the system to likely forms of heat or sound energy. Unlike the law of conservation of energy, the law of conservation of momentum is not typically observed during the sport Wepi Cikan. The law of conservation of momentum states that in an isolated system, momentum is always conserved and the total momentum of that system remains constant during the collisions of multiple masses. The law is typically not observed during the sport Wepi Cikan because there are usually no collisions that take place during this sport. The only collision that takes place is the collision between the earth and the ball. So if you really wanted to say that the law of conservation of momentum was observed during the sport Wepi Cikan, technically you can, because the collision between the earth and the ball is still considered a collision. This would be known as an inelastic collision because some kinetic energy is lost, but not all. As you can see, the ball bounces back up off the ground and it does not remain one with the earth. It is not an elastic collision because not all the kinetic energy is conserved. As you can see, when the ball bounces back up off the earth, it does not reach the same max height it did before. In all types of collisions, no matter what, momentum is conserved.
I will now be using the law of conservation of energy to calculate the velocity of the ball just before it contacts the ground. I start by listing my variables. I begin by stating the law of conservation of energy. Initial total energy is equal to final total energy. I cancel out the final potential energy because its height is relatively zero, meaning only kinetic energy will be present. I then rearrange for the final velocity and plug in my variables. I have now determined the velocity of the ball just before it contacts the ground. I can now write my therefore statement and apply significant digits. Therefore, the velocity of the ball just before it contacts the ground is 32 meters per second down. I know it's down from my diagram. I will now be calculating the impulse on the ball when it contacts the ground. The impulse is equal to the product of the force exerted and the amount of time that force was exerted for. Impulse is also equal to the change in momentum. The impulse on the ball as it contacts the ground is 68 newton seconds.
Discussing how the gravitational field affects how you play the sport Wepi Cikan. As mentioned before, if the gravitational field strength is weaker than on Earth, like it is on Mars, it would be easier to play the game as the slingshot will travel further when in projectile motion. Similarly, if you were to play the game on Jupiter, which has an acceleration due to gravity of about 24 meters per second squared, the game would be much harder to play as the stronger gravitational field strength would restrict the slingshot's projectile motion. Did you know that once the slingshot is released from the player, there is now a force of gravity between the slingshot and the player? As a matter of fact, as the slingshot travels further away, the gravitational force between the slingshot and the player decreases in magnitude.
The stronger gravitational field makes it harder to play the sport. To Wepi Cikan, I will be calculating the escape speed of the gravitational field on Jupiter and on Earth. First, we must derive the equation for the escape speed by setting kinetic energy and gravitational potential energy equal to each other and rearrange for the speed. We can now plug in our mass and radius variables for Jupiter and Earth as well as the gravitational constant to solve for the escape speed of each planet's gravitational field. The larger escape speed indicates that more energy is required to overcome the planet's gravitational field, making the sport to Wepi harder to play on that planet. Now that I have the escape speed for both planets, I can write my therefore statement. Therefore, the escape speed on Jupiter is larger for an object leaving the gravitational field than on Earth because the gravitational field itself is stronger.
The law of electric charges states that opposite charges attract and like charges repel. Let's say you were playing Tuepi Cikan on a negatively charged ground. If the slingshot was positively charged, you wouldn't do too well at the sport because the opposite charges will attract and restrict the horizontal distance of the slingshot. Now let's say the ground was positively charged. This would give you an advantage because the like charges will repel, causing the slingshot to never hit the ground. When a charged object enters a magnetic field at a velocity perpendicular to the force of the magnetic field, it follows a path of circular motion. This would make the sport, to Wepi very hard to play in a magnetic field because a charged slingshot would just follow a circular path and not go very far horizontally, which would ruin the entire purpose of the game.
I will now be calculating the radius of circular motion if a negatively charged slingshot were to enter a magnetic field. To find the direction of circular motion, I use my left-hand rules. I point my thumb in the direction of the velocity of the slingshot, fingers in the direction of magnetic field, and my palm will face in the direction of circular motion. I then make magnetic force equal to centripetal force and rearrange for the radius. I plug in my variables and get my final answer. Finally, I apply significant digits and write my therefore statement. Therefore, the radius of the negatively charged slingshot entering a magnetic field is 3 meters.
I believe that Roger Federer is an athlete who would excel in the sport to Wepi. This is because he excels in one of the most technical based sports there is, tennis. Tuepi is similar to tennis in the sense that they are both sports where technique comes first over power. In tennis, a technically skilled player would beat a powerful player any day of the week. The technique of timing your release of the slingshot in the game Tuepi is similar to the technique required in timing when hitting a tennis ball. For this reason, I believe that Federer would excel at the sport Tuepi. Also, the only physical aspect of Tuepi is arm strength from the elbow down. This is also similar to tennis. Roger Federer already has the ability to harvest energy from his upper arm and use it for movements in his lower arm and wrist, so he will be able to do the same when launching the slingshot in the game Tuepi. Finally, he has a more developed mind-muscle connection to his lower arm and is programmed to play a sport with one hand. As in tennis, you often hold the racket with one hand. He will be able to use this developed mind-muscle connection he already has to effectively use the power and technique required to be successful at the sport Tuepi.